Today's lesson is on square roots. We're going to start with some review about what are inverse operations, then looking at some inverse operations of squaring and square roots, looking at perfect squares and then non-perfect squares, and then finally how to simplify square roots. And then the process for simplifying square roots. So let's start with a simple algebra problem. 2y plus 2 equals 10. Well, the first thing I want to do is get rid of that plus 2. And by doing that, I subtract 2. And I can't do it from one side, I have to do it from both sides. So when I do that, those 2's cancel out because they are what are called inverse operations. They undo each other. Adding 2 and subtracting 2 is the same thing as doing nothing because they are inverse operations. Addition and subtraction undo each other. That's why I chose minus 2. So that gets us now 2y equals 8. And saying 2y is the same thing as saying 2 times y, or I could flip that around as y times 2. And so if it's y times 2, to get rid of that, I would divide by 2. But again, I can't divide by 2 on just one side. I have to divide by 2 on the other side. And that is because multiplication and division are also inverse operations. They undo each other. So instead of doing it this way, I'll do it the way we usually do it, which is just over 2. And again, those 2's cancel. 2y over 2 is just y, because multiplication and division, they undo each other. They are inverse operations. So I'm left with simply y equals 4. And so doing algebra is simply doing a series of inverse mathematical operations in order to isolate a single variable. I didn't want to know what 2y plus 2 was in my original equation. I wanted to know what y was. And so I did some inverse operations to get there. Therefore, you can understand that understanding inverse relationships is very important. Okay. So if we say y plus 5 minus 5, that's the whole thing is going to be equal to y, or z times 5 divided by 5 is equal to z. Because again, inverse operations undo each other. You end up where you started. So in the first equation I have y equals y. In the second equation I have z equals z. And we've talked about the fact that addition and subtraction are inverse operations, as are multiplication and division. The question is, can you think of another example? And what's the inverse of squaring something? So I know that 3 squared is 9. What does one have to do to get from 9 to 3? And the answer is square root. The square root of 9 equals 3. So we see that if I take 3 and square it, and then take the square root of it, you get back to the original 3. And that is because they are inverse operations. They undo each other. 3 squared, the square root of 3 squared, is going to be back to my original 3. They undo each other. Okay, so, and you probably know the square root of several numbers already. Like if I told you what's the square root of 16, hopefully you know that's 4. The square root of 36 is 6, and the square root of 100 is 100. That's because 4 times 4 equals 16, 6 times 6 equals 36, and 10 times 10 equals 100. But what exactly does square root mean? And let's start that by understanding why when we multiply a number by itself, we call it squaring it. Okay, so let's talk about squaring and square roots. So if I create a square that has 2 units on each side, so there's a square and it's 2 by 2, then I've created a square that has 4 square units. 1, 2, 3, 4. Therefore, we say that 2 times 2, or 2 times itself, is equal to 2 squared. Squared because it's like having a square of 2 units on a side. And we know that 2 squared equals 4. And the other way is that since a square of 4 square units has a side, or a root sometimes we'll call it, of 2, then we say that the square root of 4 equals 2. Again, because 2 times 2 equals 4. And here is a picture of this. Works for all integers, so 1 squared is 1. You can see that the 1 square there. 2 squared is 4. We've already done that one. 3 squared is 9. You can see that that's a square of 3 by 3 gets you 9. A square of 4 by 4 gets you 16. And a square of 5 by 5 gets you 25. Okay. And some numbers are called perfect squares because their square root is an integer. So 1 is a perfect square because the square root of 1 equals 1. 4 is a perfect square because 2 times 2 equals 4, or the square root of 4 equals 2. 9 is a perfect square because the square root of 9 equals 3. 16 is also a perfect square because its square root is 4, and 25 is a perfect square because its square root is 5. And you should have a good idea of what the square roots are, perfect squares are, and here is a chart of them, of 1 through 16 squared. So you should be at least familiar with those numbers, so when you see them, you can say, oh, I see that that number is a perfect square. It is x squared. However, not all numbers are perfect squares. Let's imagine if I have a box, and that box is 2 square units. So each of its sides is the square root of 2. Because again, the square root of 2 squared, their inverse operations, I'll get back to 2. So that's 2 square units. Now, let's draw our first one and 1. These are both units of 1. So that red square is 1 square unit. Then what's remaining in blue is also 1 square unit. And you'll notice that to get the 1, obviously it's 1 by 1. But to get the part in blue, I have to add 0.414213562, and actually that number goes on and forever. It's called an irrational number. I could keep writing it forever and ever and ever, and it would never repeat. It would just keep going, kind of like pi does. So the square root of 2 is not a perfect square, or 2 is not a perfect square, because the only way I can write out the square root of 2 is by writing that long decimal, and again, it will never actually stop. So because this is an irrational number, 1.414213562 ... keeps going, because it's an irrational number, if we want to say what the actual number is, what it exactly is, the only way to do that is to say the square root of 2. If you're going to say it as a decimal, you will be estimating. And so if we want to know the exact number of how big that side is, it's the square root of 2. And we have to leave it in root form because 2 is not a perfect square. So because of that, sometimes we have to simplify square roots. Just like fractions, they need to be put in their simplest form. So if you're given a fraction of 5/10, we know what to do. We realize that that's 1 times 5 over 2 times 5. So if we divide by our greatest common factor of 5 on the top and the bottom, we end up with 1/2. So if you were given the square root of 9, you need to say that that's the same thing as you need to realize as a square root of 3 times 3, because 9 is a perfect square, which equals 3. But that's, again, perfect squares, but not all numbers are perfect squares, but they can still perhaps be simplified. So for example, the square root of 18, that equals the square root of 9 times the square root of 2, which equals the square root of 9 times the square root of 2, which equals 3 times the square root of 2, and we just write that as 3 root 2, or 3 times root 2. So now let's go through the process by which you can simplify. So let's do some example problems. So if we have to simplify root 40, the first step is we need to factor whatever number we're talking about. So let's factor root 40. And so there's root 40, and I see that that's 2 times 2 times 2 times 5. So now when we factor it, we're going to rewrite that root but using our factors. So we say root 40 equals root 2 times root 2 times 2 times 2 times 5. Now the next thing is under that root, we see, are there any pairs? And so I circle whatever pairs I have. In this case, I have two pairs, or I have a pair of two 2's. Now I'm going to cross those 2's out and bring one of them to the outside, because the square root of 2 times 2 is simply 2. Now there are no other pairs there, so the final thing I do is I multiply the terms both inside and outside. In this case, there are no terms outside, it's just 2. I multiply 2 times 5 and I get 10. So my answer is going to be on the outside 2, and under the root is 2 times 5, or 10. So my answer is going to be 2 root 10. Root 40 simplified is 2 root 10. Let's try another example. Simplify root 96. Again, the first step is always to factor. So I need to factor 96. And I realize that 96 is 2 times 2 times 2 times 2 times 2 times 3. So now I can rewrite that using my factors. Once again, I have to circle the pairs. In this case, I have 2 pairs of factors. So I'm going to pull them on the outside, cross out the 2 and bring it outside, pull out another 2 and bring it outside. Now I have to simply multiply my terms inside and outside my radical. Outside, I have 2 times 2 is 4, and inside I have 2 times 3 is 6. So my final answer is going to be 4 root 6. And so if I simplify root 96, I would simplify it by saying 4 root 6.